So I'll introduce the final assignment in a bit, but we can see what Tatu did last year. So the instructions were a bit different last year, but I think the main file is in here. Yeah. So maybe you can explain it a bit.
So I work on this road traffic accident data, which is offered by Statistics Finland. And there's some explanation in here. So I wanted to find out how dangerous crossings are for pedestrians and cyclists. So basically I downloaded the data beforehand from Statistics Finland. There's a link to it here. And also I wanted it to be like, so you could run the VeriSign functions on all of Finland, since the data is sort of nationwide. So I created this on the basis of functions once again, which I imported here. So there's a separate script file with project functions, and I try to keep this main project so that there's so that it's informative, so someone can just read through this and know what's happening at each point. So I introduce the data, explain what each of these columns mean and things like that. And then I explore the data a bit. You can see all of the accidents grouped by hour, I think, yeah. When I wanted to get the accidents for a specific municipality, I call get accidents, and I imported these functions beforehand. So then I have the function here. These are just to show that everything works fine. So yeah, now I got the borders of Helsinki out. Then I join all the accidents into nodes, or I get this graph which we've been using at least I think last week's exercise. And I get the nodes out. Then I join the non-motorized accidents of pedestrians and cyclists into the nodes. And finally, once I have run all the data, find out that there was 580 accidents happening in crossings. Then I do a bit more stuff here, and finally I want to map out the data, so I use the volume module, which I've been using as well. And then I exported it, and I got the final result map. So it's an interactive map with OpenStreetMap as a background. So now every accident that happened in Helsinki can be found here. Every accident happened in zebra crossings. So we can, for example, see that there's a bit of a cluster of accidents near our campus. It's a dangerous place to cycle. And for example, there was a death in 2015. A pedestrian, I googled it, and yeah, sure enough, someone died in this crossing in 2015. So yeah, this is an example of something you could do as your final project. So I found out the data. I figured out that yeah, this should be cool. Then I worked on it, and I created the result map, and I can see that how safe your neighborhood is for pedestrians or cyclists. Something like that. Yeah.
Yeah. Thank you, Tatu, for sharing.
Yeah.
But as a quick overview for the final assignment, actually I'll show from here. So you can find the instructions on the web pages at the very bottom in here, and then here's a link to a PDF file where I try to summarize these. So if you check the instructions like 3 weeks ago, I have changed the wording a bit, but basically the goal and the contents are the same. So let's see what we are asking you to do. Grade, people are always asking about that. So it's 40% of the course grade, and the rest comes from the practical assignment. And the point of the final assignment is to still further practice the skills, the topics of this course, especially through weeks 1 to 6, and then demonstrate your skills that you have learned during this autumn. And just as a reminder, what have we learned? So we started off with shapely object, geometric objects, related methods and attributes. Then we learned GeoPandas based on our pandas skills, so reading and writing spatial files, managing projections, doing table joins, aspatial and spatial. Then we learned how to geocode and do some spatial queries, overlay analysis, reclassifying data for choropleth maps, for example, or then you could have these binary classifications of data for some purpose. And also, for example, we did these dominance areas that could be, you could apply that in the final assignment. Then we learned how to visualize spatial data using static maps, interactive maps. And finally, last week we did this network analysis and learned how to fetch OpenStreetMap data. And throughout the weeks we have used different types of data from files and from web feature services. So you can also then use all of those or select which type of data you'll be using in the final assignment. And what skills should you demonstrate in this final assignment, or what should have you all learned now? So write some Python code to start with. So test and produce modular code. Modular code refers to using functions. So don't, if you're, let's say, comparing Helsinki and Tampere, in your final assignment you should have a set of functions that you can then apply on Helsinki and apply on Tampere, not to repeat all of the code for all of the sample cases. You have learned to manage spatial data programmatically, reading data, writing data, reprojecting data, reclassifying data, overlay analysis, all these skills. Then we have learned to create the visualizations. And then finally, is designing and implementing a data analysis workflow in Python. That's of course something you'll learn then during this final assignment. And furthermore, hopefully you continue to independently search for information, so read the documentation of the tools, apply maybe new methods we haven't had time to cover here. And then of course, like especially if you wind up to some discussion forums, then see a bit that which ones of the solutions are correct. And then during the whole autumn you've learned to use version control, so also do that actively in your final assignment. And finally, communicate your work, document, so in the README file you should explain what you're doing, using markdown cells in Jupyter notebooks, doc strings in functions, inline comments, so all of that is then part of the assessment of the final assignment. And then completing assignments on time, so January 15th is the deadline if you are aiming for the highest grade. So in short, you should design or implement a toolkit, so a set of Python script files and or Jupyter notebook files that somehow automate a GIS analysis workflow. So depending on the task, it might be a bit different, but in general you'll have some kind of data acquisition block, so reading data from a file or fetching data from OpenStreetMap or web feature service. Then also data management is part of that between data acquisition and analysis, so you might have to reproject the coordinates, somehow modify the attributes, and then finally do some kind of data analysis. It might be overlay analysis, buffering, network analysis, and such. And then finally visualizing the results as maps. You can also plot graphs, histograms. Also in the kind of data exploration phase you can plot some visualizations and then some final analysis output. So here's just a bit more explanation. of the contents that should be then in the GitHub repository. Maybe this is important. So if you are using large input files, you won't be even able to upload them to GitHub, but in that case then just provide installation instructions or maybe some small sample data in the folder. So for example, the travel time matrix dataset is like 4 gigabytes, or what is it now, you know? So then either just give the link, or then you can provide like a kind of sample data structure which has maybe 2 different files, and then your script shows that it automates the process, and the same could be applied for the whole dataset. So if you need help with that, just ask. How could you handle large input files? And then remember to write readable code. So those topics we discussed more in the first period with Dave. But use informative variable names, comment your code, use doc strings, and now that we're using Jupyter Notebook files, make use of the markdown cells. So we should be, or anybody who sees your repository should be able to read the code and kind of understand what's happening, and then preferably also run the code with minimal effort with the input files maybe. So that as a guideline. But then of course if you get stuck and something doesn't work eventually, then just document what you were trying to do. Well, yeah, this is a bit arbitrary, but in principle you'll get a grade 1 out of 5, and then basically there's most of the points come from the functions and the data analysis workflow, and then a chunk of points come from overall documentation of the work. And then this kind of goes over the maximum point if you've done something extremely cool, so you can then compensate. But basically I will probably assume that your assignment is worth 4 out of 5, and then if it's less than expected, then you get a 3 or 2, and then if it's more than expected, then you get a 5. And just a checklist when if you're thinking is your submission good enough. So check that you have documented what you have done in the README file. process A, the output of that goes into process B, C, and then there's maybe a graph and a map. So this is what I mean by having some input data processing, then data analysis, and then output visualizations. And then, for example, with the access with option, the workflow might look like this. So there's several, you could loop over several input files, and then there's text files, and then there's a grid shape file. There's table join that happens, and there's the first output, travel times to destination X shape files. That goes into the comparison process, which adds a new column, which would then go into the visualization, which goes into map. So if you want, you can draw something like this. It's not necessary, but when you start to design your assignment, it might be useful to think of the main inputs, main outputs, and then the main processes. So the options for the assignment, the first one is this AccessWiz tool, which is basically a set of notebooks or Python script files for managing this travel time matrix dataset that we have been using already during the exercises. So the dataset consists of these 13,000 text files, and this tool would then work for a list of the text files and run these processes. So there would be one kind of step which finds the files based on input. Then a second process would join the input file with the grid shape file. Then one step would visualize that specific travel time matrix file, for example, travel times to railway station or travel times to the airport. And then there's another tool for comparing, for example, public transport and car, and then there's 4 other optional components. So at least these elements should be in there, and you can then decide if you could have a script file for some functions and then one Jupyter notebook for the whole process, or you might have one the script file for the functions. Then you might want to have like file finder and table joiner in the same Jupyter notebook, and then a separate Jupyter notebook for visualizing the data. So you can decide if you want to have it all in one long pipeline, or then save the output from this and then read again the output in shape files and visualize them. So there's more instructions on this on the web pages. The second topic is urban indicators, where the idea is to develop a toolkit for analyzing urban areas, and then to apply these tools at least to 2 different cases. So you could compare Helsinki and Tampere, or then Kallio and whatever else, Puistola in Helsinki. So to show that you develop some tools, and then these can be applied to different areas of interest. And you should implement, depending on the complexity, 2 to 5 different indicators. So you could check the population distribution, so reading some data from that area, do some data manipulation, table joins, maybe plot a graph and plot a map. You can also check urban population growth in that area. You could do something related to accessibility. So if it's in the Helsinki region, that can be from the travel time matrix. One topic would be green, calculating, for example, the area coverage of green areas. Some street network metrics based on OSMNX that we learned last week. Something other related to the urban form, such as building density. So there's a list of suggested indicators on the web pages, but then you can also create your own topic. So last year, I think quite a few students did then something related to urban areas, but then it got so extensive that you had only one project. I think Sakke, for example, fetched some mapillary data and calculated some statistics based on that and focused on then only that one data source. So that's one topic. You can also kind of take this urban theme and make that into your own topic, a bit like Tatu had done. This is now a bit small, the font, but if you have your own topic, such as your thesis or work project or something you're just interested in, you can design your project around that. And in principle, you should have a step for acquiring data, analyzing the data, maybe 2 different things to make it complex enough, and then a step for visualizing the data. And again, the tool should be such that it's written using functions, well documented. And if you choose to go for something totally different than the urban topic or than the travel time matrix access vis, then hopefully you would discuss it with me or Sara and Sakke before the winter holidays, just to check that it's on the right track. Yep. And finally, so there is on the web pages there's a link to a journal article related to best practices for scientific computing. So just to remind you about why we have organized this course for the first place. So to facilitate the analysis of scientific data first of all, and then geographic data in general. And of course, now that you're doing things probably for the first time, then for example this 0.6 optimized software only after it works correctly. So first you might do something that, I got the map, and then the next iteration will be that then you maybe come up with a shorter way of doing the same thing and such. So take this as an opportunity to learn, and whenever you find that you're repeating yourself, so then try to put that into a function or a for loop or something else. And always like this, test small parts of the code, make sure that they work before you continue, so that you don't get stuck. And then the last point, collaborate. So you have a room full of Python experts here now, so let's use Slack actively. On Thursday there's the practical session. Use the online forums where these things are discussed, and of course me and Sara and Sakke are here to help you if you're having any troubles. So then some additional resources. Of course, there's already a lot in the course materials now, but then of course the hunger grows as you dive deeper into doing these things. So here are some topics that we have discussed, for example, with Henrikki, but haven't had the time to include in this course. So as I mentioned, there's now this section related to raster data processing using Rasterio package on the web pages. And there is a set of notebooks you can go through. I'll provide this in the CSC notebooks later this week. What could we check? So for running these scripts you'll need the Rasterio package. But feel free to go through these materials on your own time. Then there's some cool, just for you to explore, things that have been recently developed. So there's a cool extension for pandas and geopandas called Moving Pandas by Anita Graser, where you can analyze trajectories, so movement data. There's a nice tutorial about bird migration, for example, as a Jupyter notebook file. Then Plotly Express is yet another option for doing interactive maps, so feel free to check that out. And then for raster data visualization, we found this data shader package. Let's see, with some cool hill shading visualizations if you end up using raster data in your final assignment. So that's it. Maybe final thing. So on the final assignment page, so this PDF is here, and then here is the link to the GitHub Classroom page, which is in here. So once if you're done in advance, for example, then you could do this and maybe let me know that you are finished. So if I have time before the deadline, I can also also check your assignment. But this is now not true. And then when you start working, you can, for example, then remove all of that, add your topic, my topic in here and so on, add some bullet points and such. And then, of course, commit your code, commit your script files, Python notebooks, images, sample data, or the instructions on how to download the data in here. Any questions? Repository called extra exercises if you are already bored with all these other exercises. So for example, well, this is maybe the nicer one. So in these exercises, the point is to define functions, and then I have developed some tests that call the function and see if the function returns the correct output. So if you feel that the final exercise is a bit too big of a task to start with, you can start with these. So this is a classic from the introduction to programming courses if you have taken those, but this kind of growing Christmas tree function that if I would call make Xmas tree with parameter 3, it would create this one, and if I would call make Xmas tree with parameter 30, then it would have 30 rows of Christmas tree. So then once you run these tests, you can also get some hints on how to solve the problem from the tests, so you can then check if your function works correctly. And then in these extra tasks IPYNB, so then there's a set of little functions that might, if you do these first, you could then, all of these are such that I could see that you can use in the final assignment. So again here, the suggestion is that you import the modules at the top of the script. So do that also in your final assignment. Then there is a function list files that would take a folder path and then a file extension. And in this repository there is a folder called data with some files. So then using your function that you create, for example, it should find one shapefile from the input folder, and it should find 7 text files, and then it should, this is now actually wrong because I added the Christmas tree, so it should find 2 notebook files from the root. And then there's a function for counting values, which takes a pandas data frame, a column and a value as input. Then there's a bit similar one where you should count no data values from a column, so the output should be one integer value, and you can see the correct answers in here for specific input values. Then there's a function for checking a projection, so input is a layer and an EPSG code, and then the function will check if the input layer CRS matches the EPSG code. And then finally there is a reproject layer function, which would then take in data and the destination CRS, and then do the reprojection given some conditions. So these, we won't be grading these, but then you can run these tests, and if the tests pass, then the functionality is correct. That's it. If there, I can demonstrate something if you want, but otherwise I guess that is the end of the course. Yeah, so I'm looking forward to seeing your final assignments in January. Okay, thank you.